So we talked about this last week, but I had you make some serious edits to your packets. So for this, what you're going to need is a separate sheet of paper or kind of a blank space in your packet. And if you get a separate sheet of paper, make sure you staple it to your packet, please. So what I'm going to do is just provide some notes, and a lot of this is really alluding to what we discussed in today's check-in. So you're gonna write this down, and then we're gonna go through the practice problems related to this, and it's the same thing. Right before I do a problem, pause me, you solve it, unpause me, and I'll try and prompt you. My goal is to go through all of the problems so you have a nice resource for the end of this week's quiz. Okay, so obviously we've been talking about Lewis structures, we've been talking about molecular geometry, but so far we've done this thing which is super completely fake, which is we've only drawn one particle, right? And we've done that because what we've really been looking at is the intramolecular bond, or that bond that's inside the molecule between atoms, that one right there. But in reality, this is ridiculous. I mean, we have to study it because it gives us the essence of how that particle behaves. But it's ridiculous because really you have moles and moles and moles and moles and moles and moles and moles of particles or molecules or compounds. You never ever just have one. But the shape of one dictates how they behave with each other, and that's why we're moving to intermolecular forces, not bonds, but forces. And that's going to be what is happening here or in between. And it turns out what's happening in between here is hell important. I love it because it really helps us understand science in general. And really what's happening in between has everything to do with their polarity. So let's look at a general model for this in one example, and then we're going to go through and show you how we look at it. Okay, so let's say that we had a bucket here, and this bucket was full of a non-polar compound, oxygen. Okay, so we draw the Lewis structure for oxygen here. And we know that the Lewis structure for oxygen is completely symmetrical. It's non-polar, meaning the electrons inside there are equally distributed across that covalent bond. Okay, so what's going to happen in reality when you have a bunch of oxygens together? Well, put one oxygen here, and let's say 2 equals Hella. Okay, we're always going to be talking about a ton, but we're just going to use 2. Well, where would that other oxygen molecule go? Well, because there's no partial charges here, that other oxygen molecule is going to go really far away from that. There's going to be no attraction between here. Okay, this right here, the area in between here, this is a really weak intermolecular force. Intermolecular bond, or we're going to call it a force because it's not really a bond. And the abbreviation for this is I, come on, pen, IMF. And this is what I'm going to use from now on. So it's a very weak IMF because there's no charges on here. There's no attraction between them. So what is our predictions here? Well, what state would we predict this to be in? Well, the state of matter we'd predict this to be in is a gas because this molecule is going to want to expand to fill its container. What about its boiling point? Meaning, how hard is it to separate these from one another? Well, that's going to be really low. It's going to require very little heat to separate them from one another. But let's look at another example. Let's say we took an example like, let's go ahead and do carbon monoxide. Okay. Now in carbon monoxide, we know that oxygen is more to the right on the periodic table. So the electrons are closer to oxygen, making it not negative, but partially negative, and making this carbon partially positive. So what's going to happen if these are all in here together? Now remember, because this molecule is polar, because there is a dipole in that direction, we leave these partial charges here. We don't see the partial charges there on oxygen. So what are the implications of this? Well, so far, the only freaking thing we've done in this class, I think, is positive attracting minus. That's all there really is to chemistry. By the way, there should only be one lone pair there. My bad. So, remember, we never just have one. We always have many. So if I put another one in there, where is it going to go? Well, because there are charges, these things are going to act like magnets now. And the positives and the negatives are going to line up. Right? So now we have this partially positive here and this partially negative here. And now we get a strong IMF in here before. Now there's names for these, but because we're not going to be really rushing here, I want you just thinking about it as a strong IMF. The name is actually a dipole to a dipole. But what are the implications of this? Well, the implication of the state here, these are going to be closer together. So we would assume that the state would be closer to a liquid. Now you're probably wondering, what about a solid? And let's just assume right now that the two states we're dealing with are going to be liquids and gases. Liquids when things have stronger IMFs and gases when they're weaker. And the reason is solids really have a lot to do with ion to ion or ionic bonds. So right now we're dealing with covalent compounds. And what about the boiling point? Well, the boiling point here, it would be higher than the last one, but we're just going to say high. Meaning it would take a lot more heat to separate these from one another. And that's really boiling. Remember, it's not breaking that bond. It's separating the IMF. So let's look at the ways that I'm going to ask you this. So now, if you could please open up here to the page that is part E, practice. And I'm going to walk you through one of these, and then I'm going to have you do one, and then I'm going to do it. Then I'm going to have you do one, and I'm going to do it. Okay. So species 1 is the first thing here. So what happens if we have N2? My pen is being really finicky. And another N2. Okay, so these two things came together, which they always will. Okay, this is nonpolar and this is nonpolar. So the IMF diagram, think about this box as the box that they're in. These are going to be far away from each other. They're not going to be close to each other. They're going to be far away. So the state prediction here, is it going to be a liquid or is it going to be a gas? It's going to be a gas because there's a really weak IMF there. So now let's draw H2O. We know that H2O is a bent molecule. Okay, and you can pause me right now and then unpause me. Okay, and we got 2 of them. I'm prompting you to draw 2 just as a reminder that there's always 2. But there's really moles and moles. Okay, and this is a polar molecule, and we know that's the partially negative, that's the partially positive, that's the partially positive. There's your partially negative, there's your partially positive, partially positive. Okay. Now what's going to happen here, since they're polar, they're going to attract one another. So you're going to get these things close together. This is the positive end of the hydrogen. We saw this in the warm-up today, or the check-in. And that's going to connect to the negative end on that oxygen. I'm not going to draw those lone pairs in there. And this is what gives water a high surface tension. So we can think of this strong IMF right here, drawing those slash lines to show it, as something that gives things surface tension. So when you think of strong intermolecular forces, you can think of that word surface tension. We usually refer to that with respect to water. But this is going to be a liquid. That's our prediction. Remember, gas would be when there's weak IMFs because the particles want to spread apart, and liquid when there's strong IMFs. So why don't you go ahead and pause me and try this NH3 on your own. Okay, so let's see if you guys got it right. I'm going to draw this here. Okay. So these are polar molecules, trigonal pyramidal, and now you see how connected everything is, right? You can imagine if we were in class together right now, what a huge deal I would be making about the connectivity between the molecular geometry of a substance and its polarity, I'd be grinding into you guys how this polarity thing is really, really important. So what's going to happen now? Well, the negative head of the H is going to connect to one of the positive, or the N is going to connect to one of the positive heads there. So I'm going to go ahead and just draw it kind of tiny here. Now, there's obviously moles and moles and moles and moles of these, right? Like I said. So we're just going to draw one of those moles and moles and moles of connections. So we're going to get the other N right here. Okay, and this is liquid ammonia. This is going to be your negative end, and here are your positives. I like to draw them all. Okay, and there's your strong intermolecular force because you have a positive connected to a negative right there. So this is going to be a liquid. Okay. Oh, now we have another situation here where they actually gave us, this is Cl minus. Okay, this is an ion, and it's got a full negative charge. Now, when you see this, don't freak out. Just know that negative attracts positive. So let's take a look at this. Okay, well, the first thing we have here is Cl minus, which is just Cl minus. Okay, that's an L, not an I. And then we have H2O. So we don't have to worry about the molecular geometry of that. That's just an ion. Don't trip. Negative, positive, positive. Ramsey, don't forget your lone pairs. Okay, so I'm going to draw this charge here in red. So what's going to happen with this? Okay, what do you think is going to happen? Pause me and you draw what you think is going to happen. Okay. What's going to happen here, and let me cover this up, is exactly what you thought was going to happen. The negatives and the positives are going to connect. That is all that chemistry is. There is nothing more. We put math on top of negative and positive connecting. We do negative and positive connecting. That's all it is. Okay, so that Cl minus is going to go right there. Okay, and we're going to get a very strong intermolecular force. We're going to call this a liquid. It's actually more referred to as a solution because it's a mixture of two different things, but it's going to be in a liquid state. Okay. All right, let's try this CO2 right here. Okay. And this is a nice one for us to do. So we know that CO2 is a linear molecule. We know that it's nonpolar. I draw the other CO2. Okay. So although there is a dipole in this direction and there is a dipole in this direction, those dipoles cancel each other out. So what's going to happen here is those dipoles are not going to see each other. Remember, it's non-polar, so we draw no partial charges. So there's this very weak intermolecular force. So the molecule is going to want to spread out. Okay? So this is going to tend to be a gas. Let's do SO2. We know that SO2 is a polar molecule. I forgot those lone pairs, not forgive me on that CO2. Okay, so we have two of them. Remember, there's moles and moles and moles of them. You never have just one, so the interactions between them is important. We see this in humans as well. When we talk about societies, I don't talk about my hand being bonded to my shoulder. When I'm talking about societies, I talk about how I interact with other people. Now, if my hand was not connected to my shoulder, I would not be able to shake other people's hands, right? So that's an essential component to interacting in society, my ability to signal people. But society as a whole is the intermolecular forces. A little metaphor there. All right, so this is polar. Oxygen's higher up on the periodic table than S. Now remember, if there's kind of a tie and how far to the right they are, who's ever higher up is going to be pulling harder on those electrons. If you mix that up, it's not a big deal. Okay, so do I have partial charges? Hell yes, I have partial charges. So what am I going to do? I'm going to draw my partial charges, and I'm just going to do one very simple thing. Connect negative and positive. So they have a very strong intermolecular force. Negative. So what do we think about this? Is this going to be a liquid or a gas? It's going to be a liquid. They're closer together. All right, let's try Cl2 and CO. This is a great one. Okay, so Cl2, draw the Lewis structure for it. It's going to be a non-polar linear molecule. One bond, want minus half divided by 2. Now we're going to look at CO. Now let's remember when I was talking, over here, about the definition of these intermolecular forces existing, really being very strong when they're in between polar molecules because you have visible charges, and weak between non-polar molecules because you have no visible charges, and those weak IMFs leading to molecules wanting to expand from each other. It's why when I blow oxygen into a balloon, the balloon blows up and blows up because the oxygen particles want to get away from one another. Well, I bring that up to say that I did that CO for you right there. So just go reference your notes. And now we have this really interesting situation, because what if we have a nonpolar molecule with a polar molecule? And this gets to that carbon dioxide question from the quiz. Well, you're going to have the polar molecule. Now remember that this is polar, so let's go ahead and it's partially negative because it's more to the right on the period table, partially positive. Now you have a lot of these polar molecules, and these polar molecules are going to all be aggregated together. I can't draw right now, so this is going to be like this. This is going to be like this. Okay, they're going to be like that, and they're going to all be aggregated together, but this Cl2 still will not be attracted to it. It'll be way up here, and this thing will stay in its gaseous state. Okay, now, yes, since we have two substances, we really are going to have this liquid substance down here made up of all these and this gas above. But the reason I'm going to say gas is because the state of matter of this gas has not changed. That thing, just like the carbon dioxide that bubbled out of the water, it is not attracted to this. So this is still a very weak intermolecular force, because it's like having something that's not magnetic going next to a magnet. It's not going to be attracted to it. Now for this one here, just see your notes. This is the same one I did earlier, if you remember, right here. Okay, we didn't talk about boiling point here. So what I'm going to have you do now is you're going to go through and you are going to try the rest of these here in your notes. Notice this one here, I have a star next to it. Okay, and this really has to do with ionic compounds, and I'm going to give you a little hint. This is going to be a solid. And you're not going to draw any Lewis structures here for this one. Okay, so I'm going to have you be trying this whole page on your own, and then what you're going to do is, and by the way, this is BR -1, you're going to submit a picture of that. Okay, take care.